This is the third in a series of videos that go into more detail on some probability problems. I simply entitled them More Probability Part 3. And in this one, we want to start with some vocabulary. And the first vocabulary we talked about are mutually exclusive. And that was in the last video. Mutually exclusive events are simply events which cannot both happen. And the easy definition would be, or the concise definition, the probability A and B is 0. The next one is, the next definition we talk about are independent events. And dependent events. So what we do when we talk about independent events, we say that A and B are independent if the probability of A is unaffected by whether B occurs. And what's important to realize here is this is not a philosophical opinion or a theoretical discussion. This is simply a matter of numbers. If the probability of A changes when B occurs versus when it doesn't, then we say that they're independent. Let me give you an example. Let's think about the probability that I'm happy. So the probability that I'm happy on any given day is about 43%. I can say 0.43 or 43%. That's a rough guide. Now the question is does rain affect how happy I am? Well, it doesn't a lot. I actually like rain, but I like sun too. But sometimes when it's rain, I'm late. Sometimes when it rains, I have something planned. So actually, the probability when it rains, my probability of being happy is now 45%. And if I know it doesn't rain, my probability of happy is 41%, 0.41 or 41%, 0.45 or 45%. Now, if you notice, my happiness doesn't depend that much on the rain, but it does depend a little bit, right? The probability of me being happy is changed when it rains, and therefore these are not independent. We use the word term dependent. Let's look at another example. Let's say that you roll 2 dice. And let's A be the first roll and B be the second roll. Okay? So the first thing is, what's the probability that B is equal to a 6? Well, in a 6-sided dice, the probability that I get a 6 is going to be 1 out of 6. Now let's play that experiment again and say that on the first row is a 6. And then the question is, what's the probability that I get a 6 on the second row? And here we have to really think about the structure of the problem. Does my first row have any influence at all on what my second row is? And it turns out it doesn't. So that's also 1/6. So the probability of B is the same whether or not I get a 6 on my first roll or whether or not. So we say that the 2 rolls are independent. Well, here's a key theorem that we can use. It's called the multiplication principle or property. Or principle. And we're going to do a simple one now, and we'll do a more complicated one later. So if we say if A and B are independent, then the probability of A and B is simply equal to the probability of A times the probability of B. And I could have used the term and here, the probability of A and B. It wouldn't matter. And this kind of fits our common sense. What's the probability that we flip a coin and we flip two heads in a row? Well, the only way we can get two heads in a row is we get a head and then we get another head. The probability that we get a head on the first time is 1/2, and the probability we get a head on the second row is 1/2. And they're independent, so we just go 1/2 times 1/2 is 1/4. So what's cool about probability is even what harder problems are similar to another easier problem that we can use our common sense. It works with 3 as well, so let's say what's the probability you flip 3 heads in a row? Well, if you take a coin and you flip it again, and you flip it again, each individual row is independent. So the probability of 3 heads in a row is going to be 1/2 times 1/2 times 1/2, or 1 out of 8. And that's how you use the multiplication principle, at least the easy one when they're independent. There's a harder one that we'll do later.